Well, hello everyone, and welcome back to Maths. Today we are going to be doing our first checkpoint, which means I'm going to be testing you on some of the ideas that we looked at in the past 8 lessons. So if you haven't reviewed yet, I'd encourage you to go back and try and get comfortable with the concepts, and then use this test to really gauge if you understood the concepts well or not. Because that's really important, is to study and do repetition and to get comfortable with things before you move on to the next step. Alright, in any case, have a look at these questions, try the test out for yourself first, and then we're going to go through the answers together. Wait a second, you didn't take the test, did you? Come on, go and take it. I'll be waiting. Alright, you took the test? No, you didn't. Go take it. Okay, you've taken it now, I'm sure. So let's go ahead and get into these. Alright, number 1 says, describe each of the following operations as a number line transformation. So the whole point of these last 8 lessons were to discuss all these arithmetic ideas, but as some sort of transformation to the entire number line. So what it's asking is, how do we write these operations as something that we're doing to the whole number line? So the first one, we have plus 5. So what did that do to the number line? Well, that shifts the number line 5 units right. Alright, so adding 5 is moving in the right direction, 5 units. Alright, next up we have subtracting negative 2. So subtraction, that moved the number line to the left normally, right? But because we're subtracting a negative number, that means we're going to be moving in the opposite direction as we normally do, which means this is going to correspond to shifting the number line 2 units to the right as well. Right? Subtracting a negative ended up being the same as addition. So that's the answer for part B. Alright, now on to part C. We have multiplying by 0. So do you remember what multiplying by 0 did to the number line? Well, multiplying by 0 basically took the distances between all of the ticks on the number line and compressed them down to be basically 0 distance from each other, which meant everything got collapsed into one point at 0. So it collapses the number line down to 0. And of course, if you want a more detailed explanation of these, I encourage you to go back and look at the videos for them. Alright, next up we have dividing by negative 4. So what did division do? It compresses the distance between points on the number line while fixing 0. And in this case, it's compressing the distances to be 4 times smaller because we're dividing by 4. But what about the negative portion in there? Well, whenever we divide or multiply by a negative, that is a double action, as we saw in lesson number 8. That is a double action that both compresses it, but also flips the number line. So this refers to a compresses the number line by 4 with 0 fixed. So that's the dividing by 4 part. And it flips it and flips the number line. That's the negative portion of the dividing by negative 4. So these are all 4 of the transformations for parts A through D. All right, number 2. Calculate the following by using a single number line transformation. So that means we have all of these, and we want to basically transform our number line once, and that will give us the answer to all of these calculations. So we have 3 minus 2, negative 2 plus 1, 4 plus negative 2, and 2 times negative 1. Okay, so first of all, we need to figure out what is the common transformation happening here, right? If we're going to model these with a single number line transformation, we need to have all of these actually be represented by the same thing. So let's look. Here we have 3 minus 2, and here we have minus 2 plus 1. Well, what can we do to express these as the same operation? Well, what's minus 2 plus 1? That's the same thing as 1 plus minus 2, right? We can say that since we can add in whatever order we want. And what's adding negative 2 the same thing as? Well, that's the same thing as subtracting 2, right? So we see that negative 2 plus 1 is the same thing as 1 minus 2. And that looks a lot like the form in A. Great. Let's see if we can kind of get something minus 2 in part C and D now. Well, using a similar logic for the second step in part B, what's 4 plus negative 2? Well, it's the same thing as 4 minus 2, right? Because adding a negative is the same thing as moving to the right, but then we're adding the negative, so that's going in the opposite direction, so that's moving to the left, which is subtraction, right? So we can write this as 4 minus 2. And then right here, this one's a little trickier. We have 2 times negative 1. Well, what does multiplying by negative 1 do? That's basically flipping the number line, right? We saw that in the video on perspectives on negatives. So what does flipping the number line do? Same thing as flipping from 2 to whatever the negative version is, right? But we saw that we can also express a negative as being 0 minus something. So this is the same thing as 0 minus 2, right? And we saw that we can kind of convert between these two ideas in the perspectives on negatives video, where 2 times negative 1 is the same thing as 0 minus 2. It's just we're viewing this as a flip and this as a shift. So part D is trickier, I would say, for this question, but we now have all of these expressions written as something minus 2, so now we can go ahead and use a number line transformation to calculate it. So if I take a number line here, and then I line up another one, just a copy of it, we're going to apply minus 2 to this number line, which is going to shift it 2 units to the left. So we go 1, 2, and now we just see where everything lines up. So what is 3 minus 2? Well, 3 lines up with 1, so that means 3 minus 2 gives us 1. Next up, 1 minus 2. 1 minus 2, 1 lines up with negative 1, so that means 1 minus 2 has to be negative 1. 4 minus 2. 4 lines up with 2, that means 4 minus 2 has to be 2. And 0 minus 2. 0 lines up with negative 2, that means 0 minus 2 has to be negative 2. And that is the answer to all the original things, and we were able to answer them all by using one number line shifting. All right, let's move on. Use operations to the entire number line to model the following real-life transformations. So basically, we have all of these different real-life scenarios, and we want to model them with a transformation to the number line. So let's start with number 3. It says a 7-meter-long fire truck moves backwards 8 meters. Start with the back of the fire truck at 0. Okay. So first of all, what kind of thing are we going to be doing to the number line? Well, we're looking at a fire truck moving backwards 8 meters. So that means we're going to be looking at doing what to the number line? We're going to be looking at subtracting 8 from the number line, or shifting it to the left 8 meters. So if we take our number lines here, and I'll just cross out this minus 2. I'm trying to be economical with my number line usage here. So we have a 7-meter-long fire truck. So 7 meters, and it says start with the back of the truck at 0. So the back of the truck is right here. And the front of the truck, well, if it's 7 meters long, it has to be here, right? And so those are the tires. And we have our fire truck looking something like that. It's not a very good drawing, but we've already established I'm no artist. So we have a 7-meter long fire truck, and it moves backwards 8 meters. So that's modeled by subtracting 8, right? So we're going to subtract 8 from this number line, and this will move the truck backwards 8 units. 3, 4. Okay, so the truck has moved backwards 8 units, and now we can see where it lines up with, right? So 0 is basically lines up with negative 8. That means the back of the truck is at negative 8, or 8 meters to the left of where it started. But we can also look at any point in the truck, right? Maybe at the front, that's at 7. The front of the truck is now 1 meter behind where the back of the truck used to be, right? The back of the truck was at 0, but now the front of the truck lines up with negative 1, and we can figure out at any point in this truck where that will line up with, because we moved the entire region by 8 meters backwards. All right, so that's the modeling of part 3. An accordion is stretched to be 3 times its original length. Start with the back of the accordion at 0. Okay, so we'll take our number line, and we want to stretch this out to be 3 times longer. Now, the question doesn't actually say how long the accordion is, but that's all right, because it's going to be the same thing. It doesn't matter if the accordion is, 5 meters long, 20 meters long, 1 meter long. we're ultimately going to be doing the same thing to the number line, and we can just kind of picture the accordion getting stretched out with the number line accordingly, right? So we want the back, all we care about is that the back of the accordion is at 0, and we're stretching it to be 3 times the original length. Okay. So I'm going to draw a line here. And you can do this either by taking little pieces and moving them out to stretch the number line out, or you can just draw them in. I'm going to draw them in because we've seen this many times. So we always fix 0 when we multiply the number line by 3, which is what we're going to be doing since we're stretching it to be 3 times the original length, right? And now basically the distance from 0 to 1, instead of being 1 tick, it's going to be 3 times bigger, so it's going to have to be 3 ticks. So I have 1, 2, 3 ticks. That gets us to 1. 1, 2, 3 ticks. That gets us to 2. 1, 2, 3 ticks, 3, and so on. And then same in this direction. Keeping the ticks I draw lined up with what we have up here. We have -1, -2, and -3. All right, so if we imagine that the accordion occupied this 0 to 1 space, let's say, now we've stretched out the accordion, so the space that it occupies now is now from 0 to 3 because we made it 3 times longer. So now instead of being 1 meter long, when it's fully expanded, it's 3 meters long, right? Occupying 0 to 3. All right, so that's part 4. All right, part 5. A person watches them on their phone camera squish down a gummy to be 2 times smaller. Start with the back of the gummy to be at 0. Okay, so once again, we don't actually have the dimensions of the gummy, but like number 4, it doesn't ultimately matter. We just know that the back of the gummy is at 0, and when we stretch the number line or squish the number line, in this case it's going to be squishing because we're squishing the gummy, that is going to basically compress the object accordingly, right? And we also have this added part of watching themselves on the phone camera. So a phone camera is basically like a mirror, right? And what that is going to do is it's going to reflect the image, right? So that's going to correspond to like applying a flip, right? And squishing down the gummy to be 2 times smaller, that's corresponding to dividing by 2, right? So if we have a flip and we compress by 2, what operation is this? Well, this is dividing by -2, right? Dividing by 2, that's the compressing, and the negative portion is the flip, right? It's the double action. So we want to model this, and yeah, so let's go ahead and do that. So because we're going to be squishing it down to be 2 times smaller, I am going to start with the number line that is stretched out, or where all the distances are already 2 ticks so that it's easier for me to compress it down. And so dividing this by 2 will give us essentially this number line, right? Where we've taken this number line and we have compressed it, where now the distance from 0 to 1, it's not 2 ticks, it's only 1 tick. Distance from 1 to 2, it's not 2 ticks, it's only 1 tick. So everything's been smushed down to be 2 times smaller than it was. And we also have a flip, though, that occurs, right? If we take this number line and we flip it, right, so this is the dividing by 2 and this is the flipping part, then we get the overall transformation of dividing by -2. All right, so now let's see where let's say the gummy is 2 meters long. Again, it doesn't really matter because ultimately what happened is we compressed and we flipped. But if we look at where it lines up with the region from 0 to -1. So what that means is our originally 2-unit long gummy got flipped, right? So now it's lining up with the negatives, not the positives. So that's the image being flipped or being mirrored by the phone camera. And us compressing it down means it's no longer between 0 and 2, but it's actually between 0 and -1. So it's basically 1 unit long instead of 2 units long. So this dividing by -2 models us compressing the gummy down to be 2 times smaller and what's being seen in the camera, which is actually flipping the image. All right, so that was parts 3 through 5, a little bit of kind of conceptual application of what's going on with these number line transformations and how we can actually use them. So let's go on to the next page, questions 6 through 10. All right, number 6 says, calculate the following without using a number line. So while the focus of these was to use the number line, ultimately when we're doing math out in the wild, we're not always going to be using number lines. So this is just really to check if you can do all of these fundamental and necessary arithmetic computations. So for part A, we have 14 plus -2. But what's adding a negative the same as? That's the same as subtracting, right? So this is really 14 minus 2, which is 12. All right, for part B, we have negative, 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 negative 3. So that's 4 negatives. And what do 4 negatives in front of a number mean? Well, we just look at, is it an even number of negatives, which corresponds to basically doing an even number of flippings, which takes you back to where you started, which means it'll be a positive number, or is it an odd number of negatives, which means we're going to be flipped off from where we started, which means we're going to be having a negative number. But in this case, 4, that's an even number, so we can just say this is the same thing as positive 3. We've done 4 flippings from where 3 started, so we're back to where we started with 3. All right, part C, we have negative 6 minus negative 1.4. Okay, well, what is subtracting a negative the same as? Well, subtracting a negative means we're moving left, but in the negative direction, which means we're actually moving right, so that's the same as addition, right? So negative 6 minus negative 1.4 is actually negative 6 plus 1.4. All right, what's negative 6 plus 1.4? Well, that is going to be negative 4.6, right? Because we're going in the opposite direction of the negative, so negative 6 plus the 1 of 1.4 will be negative 5. And then we're just removing another 0.4 from the negative 5, so that gives us negative 4.6. All right, and then for D, we have 4 times negative 5. So what's a positive times a negative? It's a negative, right? Because the multiplying by a negative corresponds to the flipping action that we saw. And we're flipping from positive to negative, so our answer is going to be negative. And then we just look at the number parts. What's 4 times 5? Well, that's 20. So 4 times 5 is negative 20. All right, that was part 6. Part 7. We'll calculate the following without using a number line. So these ones we have some we have multiple operations happening in a single expression. So we have 6 plus negative 2 minus negative 7. All right, so let's simplify this a bit. What's adding negative 2 the same as? Well, we saw it in 6 part A. That's the same thing as subtracting 2. So this is 6 minus 2. And then what's subtracting negative 7? Well, we saw this in 6 part C. Subtracting a negative is the same as addition. So we get 6 minus 2 plus 7. And when we combine these, we have 6 minus 2, which is 4 plus 7, and that is going to be 11. All right, part B, we have negative, negative, negative 5 times negative 3 times negative 4. All right, so to start off with, what's negative, negative, negative 5? Well, this is 3 negatives, or an odd number of negatives, which means we're going to be flipping 5 back and forth 3 times, which means we're going to end up on negative 5, right? Odd number of negatives gives us a negative number. So this simplifies to negative 5 times negative 3 times negative 4. All right, now at this point, we can say, okay, what is negative 5 times negative 3? Well, negative 5 times negative 3 is a negative times a negative, which will give us a positive, right? Since multiplying by a negative number includes the action of flipping from the, in this case, negative to positive. So this is going to be a positive number. And then let's look at what's 5 times 3. That's 15. So we get positive 15 times, and then we have negative 4 right here. Okay, so now we're looking at a positive number times a negative. Again, multiplying by a negative, that's a flipping action. So we're going to be going from a positive number to a negative number because we're multiplying by a negative here. And we need to know what the number amount is, so what's 15 times 4? You may know this, you may not in your head, but if you don't know it, we can quickly do it on the side here. 5 times 4, that's 20. Carry the 2 up here. What's 1 times 4? That's 4, plus the 2 we carried is 60. So our answer is going to be 60, but it's going to be negative 60 because it was a positive times a negative. And another parallel to notice here is we have 3 negatives multiplying each other, and we got a negative answer. That logic is very similar to how when we had 3 negatives, that's an odd number of negatives, it produced a negative number. All right, moving on to number 8. So number 8 says, what can I subtract from the number line, and what can I multiply the number line by such that they do the exact same thing to the number line? So what does subtraction do to the number line? It shifts it back and forth, right? If we're subtracting a positive number, it shifts it to the left. If we're subtracting a negative number, that's the same as addition, and it shifts it to the right. But the point is it's a shifting, right? So every number gets slid to some different place. And multiplication to the number line, what that does is it takes the number line and it stretches it, right? But it keeps 0 fixed. So the question is asking is, when is sliding the number line and stretching the number line, when can those be the same thing? And you might think, well, is there even a case of that? Since when we slide the number line, everything, including 0, gets moved, but multiplying the number line means we're going to be stretching the number line out, so the distances between numbers move, and that doesn't happen with subtraction. And 0 doesn't move at all, and with subtraction, we saw 0 does get shifted. So in this case, we actually have to think about when are these number lines going to be the same? Well, the number lines are going to be the same when we've done nothing to the number line, right? So if we have two number lines and we do nothing to both of them, obviously they're going to be the same number line, right? So now the question is just, how do we express doing nothing to the number line with subtraction, and how do we express doing nothing to the number line with multiplication? So subtraction, if we subtract 0 from the number line, that's going to keep the number line perfectly still. It's not going to do anything, since anything minus 0 does nothing, right? So the number line will stay the same in that case. And then what can we multiply the number line by such that it doesn't move at all? Well, if we multiply the number line by 1, that's also not going to change the number line at all because all the distances between two numbers are going to be the exact same. So if we subtract 0 from the number line, it does nothing, and if we multiply by 1 to the number line, it does nothing, which means those two number lines will give us the same thing. All right, let's go on to part 9. I stretch a 2-meter long slinky to be 2 times as large. Okay, so that looks like multiplication by 2. I first model the slinky on the number line by fixing the back of the slinky to be at 0 and the front to be at 2, and then I stretch it. Okay, so what's meant by that is we take a number line and we put the slinky between 0 and 2, like this, and then we stretch out the number line and we see that the slinky gets stretched out along with it, and it becomes longer, right? But then it says, in a second case, I model it again by this time as fixing the back of the slinky to be at -1 and the front to be at 1. So the second case looks like this, where the slinky, it's still 2 meters long, but it is now between -1 and 1, right? So if it's between -1 and 1, when we stretch it out, it's still going to be stretched out to be 2 times longer, just like here. So both instances where we have these different starting positions and we stretch it out to be 2 times as long, we still get a stretched slinky and it still works. But the question is if I am at 0 in both cases, what do the two different positions for the slinky represent? Okay, so it's saying that I'm at 0, right? And I'm the guy stretching the slinky, right? So what do these two different stretches represent, right? They both represent stretching the slinky by 2, but they are modeling something different if we consider this problem relative to 0. So if we think of me in the middle, and I don't have a slinky, so I'm going to use a rubber band instead. If we think of me in the middle, and we're stretching it out to be 2 times as long, the first case where I'm at 0, then stretching out to be 2 times as long would look something like this, where I don't move the slinky to the left at all, right? I just move it to the right. Whereas in the case where it's between -1 and 1, and I'm still in the middle at 0, then when the number line gets stretched out, because 0 is fixed, right, when we stretch the number line, what that's going to look like is going to look like a stretching like this. So both cases, yeah, they model stretching the slinky by 2 when we stretch out the number line. It's just because we're focusing on the point of 0, which is the fixed point when we stretch the number line. That is going to basically represent something a little bit different physically, namely how I stretch the slinky. So it's either stretching it like this in the first case or stretching it like this in the second case. In both cases, I'm stretching it to be 2 times as long. Alright, so I hope that one made sense. I think that's a pretty interesting problem. Alright, and we're just about done here. You're doing great. Let's look at number 10. Alright, so it says, I walk 10 meters to the left of where I started. How can we express my positional change in terms of a negative number? Okay, so 10 meters to the left, that's usually represented as -10 if we think of negative being the left direction, which it's wanting us to since it wants it in terms of a negative number. So -10 is the negative number that we're thinking of. And it says, would it make more sense to think of the process as 0 minus 10 or 10 times -1? We see that, of course, both 0 minus 10 and 10 times -1 are two perspectives on a negative that will give us -10, but the question is which is more relevant to the situation. So if I end off at -10, and it's 10 meters left of where I started, that means I started at 0. So I would think that 0 minus 10 is actually the perspective that would make the most sense in this situation, since I'm not really talking about reflecting from 10 or anything like that. It's just I simply started at 0 and I moved 10 meters to the left, which gave me negative 10. So in this case, it would make more sense to think of it as 0 minus 10. All right, well, that was the test. How did you do? If you had some trouble with it, that's all right. You feel free to ask any questions in the comments, and you can also go back and review some of the videos that you found that you were weak on. But in any case, next up, we're going to be doing a dive into fractions, something that students tend to struggle with a lot. So I want to give that a good amount of treatment and give you some various perspectives on how and why things are the way they are. But that's going to do it for me today. Have a good one, stay groovy, and I'll see you in the next video.